Hi everyone, we're Team 8 and our project was the development of a smart shunt system for patients with hydrocephalus. We will first start by defining the problem and our main project goals. We will then go over the improvements our team made in future work.
Hydrocephalus is the abnormal accumulation of cerebrospinal fluid in the ventricles of the brain, which can be seen in Figure 1. This condition occurs in about 2 of every 1,000 live births. The main treatment for hydrocephalus is placement of a shunt. This shunt redirects the excess fluid from the brain to either the thoracic or abdominal cavities through a catheter, which can be seen in Figure 2. A 2014 study states an overall shunt failure rate of 46.3%, which is due to blockage, overdrainage, underdrainage, or infection, and that is the motivation for a better device.
Cerebral shunts have very high failure rates, which if left unrevised could lead to increased pressure, brain damage, and death. Currently, there is no non-invasive way to assess shunt function, which leads to frequent hospital visits due to the uncertainty of the device. The main goal of the smart shunt system is to provide a non-invasive way to evaluate commercially available shunts. The system will provide continuous CSF flow rate data and have contaminant detection abilities. Using Bluetooth, this data will be sent to a patient's smart device in real time. To continue the development of the smart shunt system, we chose to focus on the patient. To do this, our goals were to provide meaningful data for continuous evaluation of shunt performance. We also wanted to improve the implantable sensor housing unit and external unit for long-term monitoring. Lastly, we wanted to create an app that would allow the user to understand their shunt functionality. Our smart shunt device will provide valuable data, which will allow the patient and healthcare provider to immediately know whether the shunt is functioning properly without invasive tests. This will lead to less hospital visits, will save the patient money, and will give the patient peace of mind that their therapy is working.
This graphic shows the flow of the smart shunt system. So starting in the brain, cerebrospinal fluid flows into the shunt and then into the sensor housing unit. Information about shunt function, such as CSF color and flow rate, are sent to the transmitter. This information is sent through the skin using IR frequency to a receiver. Then it's sent to the external unit where the Bluetooth module relays the data to an app on a smartphone. On their smartphone display, the user can read their flow rate and check for debris in their shunt in an easy-to-read format.
One of the main areas of improvement we have made is to the internal unit. We were able to simplify the design to have less parts for easier assembly and decrease the total volume by approximately 40%. A main challenge with last year's design was CSF leakage out of the housing unit, so we added a rubber seal and lip groove connection to prevent leakage. The sensor housing unit is an important part of the smart shunt system because it holds the flow sensor as seen in the exploded SolidWorks model.
In order to mill the sensor unit, we imported our STL files to the CAM software for the Roland SRM 3-axis mill. The rectangular stock is clamped using tape and the tool is brought to the 0 position in the work coordinate system. From here, the G-code generated by the CAM software is run and the design is machined. The design was complex due to the cylindrical inlet and outlet channels. The bottom component had to be reclamped twice in order for the mill to get all required faces. As the one-way valve in the hydrocephalus shunt discharges, the cantilever beam in the sensor deflects. The changing angle of incidence from the light source increases the intensity of the deflected light onto the photosensor. This signal will show the rise and fall of the cantilever, which responds to the flow rate through the shunt.
On the left is a SolidWorks model of the external unit, which holds the rechargeable power block and Beetle Bluetooth module, and the lid is shown on the right. The slim design was chosen so the patient could comfortably fit it in his or her pocket and wear throughout the day.
Connection between a Beetle BLE Bluetooth module and an Android smartphone was established, as text and numerical data transmission was produced through the process. The plot above simulates a continuous sine wave using Arduino software code, and it approximately represents a normal CSF flow rate for a patient. Even though we are currently sending sample data now, we are working on incorporating the smartphone app with the sensor housing unit so that we can receive real-time flow rate data instead of preset data. The smartphone application also features an interactive layout for a patient and has capabilities to transfer that data to a physician in the presence of abnormal CSF flow rate values.
We were able to create a spectrophotometer that could detect the concentration of red dye in a solution. However, we are still working on implementing this concept into the sensor housing unit. One of the next steps should be working on data processing methods to detect contaminants through absorption spectroscopy. We would also like to manufacture the device with better performing biocompatible materials. There are a variety of materials currently used in medical devices. The current model was made using ABS because of time constraints, but it was intended to be made with acetyl and acrylic plastics. Ideally, more advanced medical-grade plastics should be used when this device is in trials.
We would like to thank our advisor, Professor Hoshino, and our teaching assistants, Martin and Madi, for supporting us throughout the development of our project.